Okay, this is the fourth video on Chapter 7 and 8, the Intro to Quantum Mechanics. Where I left off on the third video was the solution to the wave equation showed that the discrete quantum states actually were represented by three quantum numbers. By the way, I never, maybe I didn't do this properly, but in the earlier diagram, the earlier theories, starting with Planck's and also in Bohr's atomic model, there was indeed a quantum number, but it was only n. We never introduced the second and third one that fell out of the wave equation. And so, anyway, I just want to put that in context. So, what I want to do now is I'm going to kind of, first of all, I want to draw a few things. The relationship between n, l, and m was a little strange, if you remember mathematically. There was the L and M, the ranges of L and M kind of varied by according to how big n was. So I want to kind of draw some things here, and I think I've actually showed you some of this before, but I kind of want to capture this down here before I even talk about the shapes. So from the Schrödinger's equation, for when n equals 1, the number of discrete states that we can have, which by the way we always know is going to be n squared, which is interesting also, and that falls out of the math as well. But there's going to be one state, and the quantum numbers are essentially, and I'll draw this in. Actually, let me switch pens to a better pen. I'm going to draw this as a series of three numbers, basically the n, the l, and the m. And if you remember, it's kind of small here, I'm not sure if you can see it, but the n is always numerically increasing starting at 1. L is ranging from 0 to as big as n minus 1, and then m ranges from minus l to plus l. Okay, so the quantum numbers for this one state are n equals 1, L equals 0, and M equals 0. And that's it. There's only one state, and there it is. So it's represented by 1, 0, 0. And in the subsequent rows, I may leave off the little curlies. So when we see three numbers separated by commas, those are the quantum numbers that represent that all of the states that are possible. Okay. So let's go on now to 2. When n equals 2, the number of states is going to be n squared 4. I'm going to draw this differently. I'm going to draw this as 1 plus 3, and you'll see why in a second. But sure enough, there's 4 states when n equals 2. And the states are n equals 2, and L equals 0, and M equals 0. Okay, that's one state. Then there's also n equals 2, L equals 1, and then m takes on one of its three values. Negative 1 is one of them. And then 2, 1, and then the other m value, 0. And then finally 2, 1, and the third value for m, which is plus 1. Okay. So I'll draw a little line here. But you can see that the possible orbital states for quantum states, orbitals, I don't think I ever used that term, but orbital is a term that was kind of used as an extension of the original Bohr's model that were orbits. When we switch it to this wave model, we call those discrete states orbitals. So each discrete state is a certain orbital. So in this case, the number of orbitals is 4, and each of the orbitals is described by different sets of these three quantum numbers. Okay, and sure enough, there's 4 of them as we'd expect. We go on to the third one. So when n equals 3, the number of states is going to be n squared, or 9. I'm going to draw this as 1 plus 3 plus 5. Okay, and you'll see why in a second. By the way, hopefully you can see here is that my dog is barking. Be quiet. These 4 states kind of break down into 1 where L is 0, and then the other 3 is where L is valued 1. So that's why it's kind of handy to draw it as 1 plus 3. All right. Let's see if I run out of real estate on this one. I might, in which case I can fudge this line a little bit if I need to. So the states, actually, you know what I'm going to do? I'm going to draw a little line in the middle here. So the states are first n equals 3, and L equals 0, and M equals 0. There's our 1. In fact, you probably remember that. Same sort of pattern on all of these when L is 0. Okay. But then we have 3 others, which is when L has the value 1, And just like the other ones, it's -1 for one of them, and then 0 for the second one, and then, well, I'm talking about m values now, and then 1 for the third one. So this is 1, here are 3, and the last 5 will be when n equals 3 and L equals now 2. Remember, L can go as high as n minus 1, so sure enough, L is 2. But when L is 2, we can have, for values of n, values that range from -2 to +2, which, by the way, is 5 of them, if you think about it. -2, -1, 0, 1, and 2. It's 5 of them. And that's going to fill out our last 5. So we got 3, 2, -2 is one of them. 3, 2, -1 is the second one. 3, 2, 0 is the third. 3, 2, 1 is the fourth. Finally, 3, 2, 2 is the fifth. Okay. So sure enough, there are, for n equals 3, there are 9 orbital states, quantum energy states, discrete states, that are possible that match, that have the quantum numbers like this. Again, at this point, this is all just pure math. In fact, you can think about the whole wave equation and even the whole notion of L, M, and N, L, and M as really just solutions to a mathematical equation. And again, that mathematical equation happens to be a model of electrons as though they behave as a wave. But this is, at this point, just a solution. I'm going to draw one last one for M, and I'll probably leave off some of the math so I don't have to be so tedious with drawing it. But when n equals 4, the number of states would be n squared 16. I'm going to draw that as 1 plus 3 plus 5 plus 7, okay, which is indeed 16. And the number of states that we're talking about here, and we'll probably get rid of this line, is first, we remember good old 4, 0, 0. That's when n equals 4, L equals 0. Be good now, dog. And of course, m equals 0. There's our 1. And we have 3. That will be 4 and L equals 1. And, you know, m can have 3 different values. -1, 0, and 1. There's our 3. Okay, be good now. Then I'll have my 5er, which is n equals 4, but now L equals 2. And then the m is going to vary between -2 and +2. So there's 1, there's 2, there's 3, there's 4, and there's 5. And then last, for the 7th, we'll have n equals 4 for the 7 states. N equals 4. Now L can equal 3. And then the m value can vary between -3 and +3. I'm going to draw that one, and I'll draw the last one. And there are 1, 2, 3, there's 5 in between that I'll leave out. So sure enough, we have 1 plus 3 plus 5 plus 7. And this continues. We could do n equals 5 and keep on going. And it's the same sort of pattern as we go. Again, this just falls out of the math. Okay. All right. Now, the other thing that falls out of the math is the shape of these, the various shapes when L goes, and not just shapes, but shapes and orientations for L and M, for how L and M vary. So I want to cover the shapes as well. I guess I'm going to do that in the next video. Okay, stop this.